All right, I wanted to go through the problems that you've been working on this week to make sure that you understand how to do the different processes. Oh, there were no questions. Forgot that I had those slides there. Sorry about that. All right, so this was the first question, which is the mass sliding down an inclined plane. It does have an external force applied to it, and basically we're told the present position as it's shown, the spring is not stretched or compressed, so that could be our equilibrium position, and it really does work best if we sort of take this to be our x and it's measured from that initial position, and you'll see that as we go through. We're told that when it's at that location, it has a speed of 5 meters per second, and we're trying to find how far will it go until it comes to a stop. I found that using the work kinetic energy theorem, it worked for me. You can use conservation of energy. Keep in mind that this U in this expression means work. I think I'm used to it. You need using U for potential energy, so when I look at it initially I get confused. So if you're in that boat with me, it's work. Work is equal to the change in kinetic energy. The reason I don't like conservation of energy for this problem is because that external force of 100 newtons is not a conservative force, and so we would have to account for the work that that force does in our expression. And so I like this idea first. So basically, what is the work that is done? The work that's going to be done, let's just list the things first. There'll be the spring, there'll be gravity, and there'll be that external force. The change in kinetic energy is going to be 1/2 mv final squared minus 1/2 mv initial squared, but if it's coming to a stop, that first term is 0. Okay, so now let's write the expressions for the work done by the spring and by gravity and by the force. So I actually wrote the work done by the external force first, which is just 100 newtons times the distance that the block is going to move. And then the work done by the spring is listed as 1/2 kx initial squared minus 1/2 kx final squared. And then the work done by gravity is mgy initial minus mgy final. And all this is going to be equal to minus 1/2 mv initial squared. So those expressions for work done by the forces are things that we saw in the lecture. So the for this thing, what we could say is the initial stretch of the spring is 0, because we're told that at this distance of s equals 0.6, it's not stretched or compressed, so there's no spring energy in that term, so we only have whatever it is in the final position, which is just our x. And then if we sort of if this is the final position, we could use that as our y equals 0, and so the y initial would end up to be, if this is our angle of 30 degrees, it could be expressed as x sine of 30 degrees would be the y value. So using those things, I can simplify this expression a little bit. 100x minus 1/2 kx squared plus mgx sine of 30 minus 0 equals minus 1/2 mv initial squared. All right, so if I'm substituting in some values, I have 100x. My spring constant is, what is it? Oh, it's 200. 1/2 times 200 x squared. The mass is 10 kilograms, 9.8 x sine of 30 equals 1/2 10 times 5 squared. All right, I'm going to go to the next slide to simplify this. I have minus 100x squared plus 100x plus 49x equals minus 125. So those are the terms that I get once I put in all my numbers. So I wanted to simplify this, and I'm going to move everything over to the right-hand side. So I'm going to get 100x squared minus 149x minus 125 equals 0. And then I'm going to divide by 100, x squared minus 1.49x minus 1.25 equals 0. Then I'm going to use the quadratic formula. And from those values of x, I really only want to use the positive one. This simplifies to 1.49 plus or minus 2.69 divided by 2. And I got 2.09 for my x. But then the total distance, s, is going to be s initial plus this x. So that's 2.09 plus 0.6, so my value is 2.69, is the total distance that it's moved. So hopefully that makes sense. I think most people got that relatively easily once you got organized. Our next problem was more a strict conservation of energy with a little bit of projectile motion. So the 2-pound brick is going to slide down the roof. It has a velocity at point A of 5 feet per second, and we want to know the speed at B. Because it's a smooth roof, we can assume there's no friction, and so we can use conservation of energy. And we'll set the kinetic energy plus the potential energy at A is equal to the kinetic energy plus the potential energy at B. So at A it's 1/2 mva squared, and I'm going to use B as my y equals 0 for this part of the problem, and so it has a gravitational potential energy of mgha. I want to know what its speed is at point B, and because I use point B as my y reference point, it doesn't have any gravitational potential energy at point B. When I'm putting in values, I could have simplified this. I just wanted to point out that the 2 pounds was a weight, so we'd have to divide by the acceleration of gravity in feet per second in order to have the mass. We could use mg as the weight, and so I could just have 2 times the 15, because 2 is the mg, and then I'll have also here 1/2 2 over 32 VB squared. So, rearranging this, I did a little bit different in my notes, but VB solves to be 31.4 feet per second. So that one was pretty straightforward. If we look, the second part of this problem asks us to do 2 things. We want to know what is this distance d, and then also what is its speed at c, which we noticed wasn't labeled, so we're going to assume it's right here. So I'm going to do that part first because it's easier, and I'm going to use conservation of energy between B and C. This time, I know the speed at B from the previous part, and I'm going to use C as my reference point, and so the potential energy at B is mg times 30. Oops. 1/2 mvc squared, and then it doesn't have any gravitational potential energy at point C. So I could solve. This time I'm going to be different, get rid of the mass. I'm going to multiply everything by 2, so I have VB squared plus G times 30 times 2 equals VC squared. VC, if I do my calculation, ends up to be 53.9 feet per second. And I think I might have put meters per second in the last slide. So fix that mentally for yourself. Now, how do we find the distance D? So we know that when it leaves the roof, it has a speed of v sub b, and the angle that it makes here, theta, is the same as this angle, theta. So we can use that triangle to help us write the components, because what we want to do is we want to use the kinematic equations to help us solve this problem. So it doesn't erase well, so that's why I scribbled it out. So those are our kinematic equations, and let's put our values in here. X is equal to, and my velocity was, at B was 31.4. The cosine of theta I can express as 4/5 using the triangle. In the y equation, my initial y is 30. The y velocity is negative. It's 31.4 times 3/5 is the sine of theta, and minus 1/2 32 t squared. So I'm going to first, what I'm going to do is, if I want to find the time of flight, because if I use that in the x equation, I could find d. That's the distance it goes. So the time of flight is given, like when it hits here, y is 0. And so that would be equal to the 30 minus 18.84 t minus 16 t squared. Using the quadratic formula, t I found is 0.9 seconds, and that's the time of flight. And if I put that into this equation, I'd find the x, or the range, which is my d, and that I found to be 22.6 feet. So hopefully that makes sense. All right, almost halfway done. All right, so in this problem, this was kind of weird, but we have this 4 kilogram collar, which is this thing right here, and it has a velocity of 2 meters per second at point A. Now, it doesn't actually show it at point A, but that's where we're starting with. So it's attached to the spring, and so as it goes around that curved pipe, it's going to stretch, and so we'll have to think about both the elastic potential energy, and also it's going to change its height, so we'll also have to think about its gravitational potential energy. So we're going to write this as the potential energy at A plus its kinetic energy at A is equal to the potential energy at B plus the kinetic energy at B. And we're going to let this be our y equals 0. When it's at point A, it's going to have a potential energy, mgha, and so notice that this portion is like a semicircle, well, it's a quarter circle. So the distance from A to the central point is going to be 0.4. It's also going to have some sort of kinetic energy. Not kinetic energy, elastic energy, due to the fact that it's compressed or stretched. So we're going to let that be x sub A for right now. At B, it's not going to have, and it also has kinetic energy. At point B, it's not going to have any gravitational potential energy, but it's going to have some elastic potential energy. And then I'm trying to figure out what its kinetic energy is at that point. All right, so at putting in some numbers, it has 4 kilograms, 9.8. It's 0.4 meters off the ground, or off of point B. The spring constant's 400. Now, we're told that the unstretched length of the spring is 0.2 meters. And so if I want to measure x as measured from the equilibrium position, what I'd have to do is notice that when it's at point A, the length of the spring is 0.1, but I need to subtract a 0.2 and then square it, because I'm going to need to subtract that 0.2 from any to find the length. Then I have 1/2 times 4 times 2 squared. Now, when I look at the elastic potential energy at B, now at B, I'm going to imagine the spring is going to be like this, where it's like part of a triangle, which this side is 0.4, this is 0.3, and so this side would be 0.5. It's like a 3, 4, 5 triangle, which means that the total length of the spring is 0.5, but I have to subtract its natural length, which is 0.2. And then I have its kinetic energy. And it doesn't have any gravitational potential energy at that location. So those are the numbers that I would use. And if I rearrange everything and solve for the velocity at point B, I should get 1.96 meters per second. The hardest part about this one is figuring out what the proper x is to use for the spring, and also seeing, just how everything is oriented and what it's going to look like when the collar slips down to point B. All right, so last question was the roller coaster question, which I think threw some of you for a loop. So the question is, how high does the roller coaster have to be at point A so that when it goes around the loop at point B, it doesn't leave the track? So this necessitates us to use a combination of force expressions and conservation of energy, because how do we know about leaving the track? You should know instinctively that if the car goes too slow as it goes around the loop, it'll literally fall out of the loop. What are the physics involved? Well, let's just look at it, assuming in the case that it doesn't fall out of the loop. We're looking at forces in the radial direction because as it goes around in a circle, it has centripetal acceleration. In this case, the two forces that I identified is the normal force, which is the force that the track exerts on the car, and the force of gravity. Those both are pointing in the same direction. They're pointing down, but that's also the direction of the acceleration. So I'm just making them all positive instead of making them all negative. It doesn't really matter. If it leaves the track, the normal force goes to 0. And so this sort of sets up for us a way to find the speed at the instant when it would leave the track. And so that becomes like the minimum speed that it has to have. If I rearrange this, we can say that v squared will be g times r. So I'm going to use that in a minute. That's the velocity it has to have at point B. So now let's look at conservation of energy between points A and B. Point A has some height, that's what we're looking for. It doesn't have any kinetic energy. Kinetic energy at B is 1/2 mvb squared, and it's going to have potential energy of mghb. Now some of these things we know. We don't know the height at A. Now, we actually calculated how fast it would have to be going at point B. We found that VB squared would be G times R, so we'll just substitute that in. And then mg times 20. All right, so we're going to eliminate mass, divide by G, and HA can be expressed as 1/2 R plus 20, and so that ends up to be 7.5 over 2 plus 20 is equal to 23.75. And there we go. Well done. Hopefully that helps, and see you next week.